Kathy's Gatos here. In this lesson, we are going to look at using logarithms to solve exponential equations. So I want to take you back to lesson 1 of this unit, and this is where we started solving exponential equations by using a common base. So for example, if I have 2 to the x equals 32, and I want to write that using the same base, I go to the smaller number, which is 2, and see, can I write the larger number as a base of 2? So here's my powers of 2, and I can see right here that 2 exponent 5 is the same as 32. So 2 to the x equals 2 to the 5. And then remember I used my really bad joke to make like a DJ and drop the base, and then x equals 5. Let's look at the next example. So 4 and 2 are the bases. Again, go to the smaller base, and you can see that 2 squared is the same as 4. So I can write the left-hand side as 2 squared to the x equals 2 to the x plus 3. So this will be 2 to the 2x equals 2 to the x plus 3. Again, make like a DJ, drop the base. So I can solve for x here by subtracting x from both sides, and I get that x is equal to 3. Okay, let's look at a question like 2 to the x equals 50. Now, this cannot be written as a common base of 2. So the solution can't be written using powers of 2 because 50 is not a power of 2. If we look at our powers of 2, 50 is in between 32 and 64. So I know since 50 is in between 32 and 64, that means that 50 is in between 2 exponent 5 and 2 exponent 6. So I think 50 is closer to 64, so x will be closer to 6. I don't know, let's say 2, sorry, let's try that again, not 2, 5 point, I don't know, 7. This is a little guess, okay? So that's just giving me an estimate. If I want to figure out a better way of doing that, I need to switch to log form. So this is where logs come in handy. If I can't solve an exponential equation using exact values, using common bases, I'm going to use log form. So I love logs, no lie. Because I love them so much, I call them my bae. And that helps me switch from exponential equations to log form. So exponential equations to log form. Here's what I'm going to do. I'm going to use the acronym of BAE to help me do that. B stands for base. The base of an exponent and a base of a log are the same. A stands for answer, and E stands for equals exponent. So what I mean by that is if I have b to the x equals y, there's my exponent. If I want to write it in log form, I use BAE. So log, B stands for base, A stands for answer, the answer was y, E stands for equals the exponent, which was x. So by switching it to log form, now we can have an exact value and get a better idea of what that exponent answer actually is. So let's try this. We want to find an exact solution, which just means no decimals. So we're going to convert to log form, of course, by using BAE. So if I have 2 to the x equals 50, switching it to log form, I have B stands for base, A stands for answer, E stands for equals exponent. This is my exact solution using no decimals. So let's see how good my approximate solution was when I guessed over here. I guessed it to be about 5.7. So we'll see if I'm even in the ballpark. So put that into my calculator. Hey, not too bad. I got 5.6 is the approximate answer. So my guess of 5.7 was pretty close. So this would be my exact answer, exact value, no decimals. This would be my approximate answer. I say approximate because that decimal keeps going. So it's a non-ending, non-repeating number. So that's why it's an approximate, because we are rounding it. So let's use this idea of BAE to solve other equations. And that's what I want in exact form. So if I have 4 to the x equals 7, let's use BAE. So log base answer equals exponent. So that is my exact value. Now I can leave it as log base 4 of 7, or I can write it as log of the argument divided by log of the base. So two different ways that I can write that. Again, this was the way that the 84s put it in their calculator. This is the way the 83s put it into their calculator. Now, if I wanted to know what that was as a decimal, I would just plug that into my calculator. And it said it wanted it as a decimal to 3 decimal places. So that would be 1.404. The 6 tells me to round the 3 up to 4. So about 1.404. Okay, let's try the next one. I have 8 exponent x plus 4 equals 40. Now this looks different than this because the power is not isolated. So we need to isolate our power first. So I'm going to subtract 4 from both sides. That's gone. So I have 8 exponent x equals 36. Now 8 is not a power of 36, so I can't use common base. So let's switch to log form using base answer equals the exponent. I can write it that way, or log of the argument divided by log of the base equals x. So that's my exact value. If I wanted to know what my approximate value is, I just put that into my calculator, and to 3 decimal places, it would be approximately 1.723. Okay. Let's look at a word problem. So in this one here, according to StatsCan, in the 21st century, Canada's population has been growing at an average annual rate of about 1%. The exponential equation can be used to predict the population, P, n years after some known population. So if the Canadian population at the beginning of 2001 was approximately 3 million, so that 3 million is going to be the amount that I'm starting with. That's going to be P sub 0. Estimate the year in which the Canadian population will reach 50 million, assuming, that's a big assumption, the same average annual growth rate. So here's my formula that I have, substituting in 30 million for my original or initial value. This is an example here of y given 50 million and x needed. So anytime we have y given x needed, the only place y can go is in y equals. So this is an example of y1, y2 intersect. So in y1, I put my exponential equation. In y2, I put my given value, which is 50 million, and then I find out where they intersect. So you can see here they intersect at 51.3. So the challenging part always comes when we have to decide how should we round. So looking at this, this really means 51 and a bit of a year. So it's going to happen partway through 2052. So 2001 plus 51 is 2052. So it's going to be partway through that year. That's where the little bit comes in. So this is what I mean by a bit. Okay? So the main objective in this unit, of course, is to solve exponential equations using algebraic technique. That's where the change of base, the log form, comes into. A graphical solution is always really good to check. So I always like to check my answer graphically. So if I wanted to check the answer to 4 exponent x equals 7, I can use an intersection method. That's y1, y2 intersect. So y1, y2 intersect, you can see where they intersect at 1.4. And that's approximately the answer that we got. So let's solve exponential equations using logs when we have 2 exponents, 2 powers. So whenever we have 2 quantities that are equal, the logs of those quantities are also equal. So what we can do is take the log of both sides. Now when I take the log, it's a common log. It has a base of 10. So taking the log of both sides. Whenever you have a power equal to a power, by taking the log of both sides, watch what happens. Log of a to the m equals log of b to the n, using power law, this exponent comes down in front. So if a to the m equals b to the n, in other words, they're just two different powers with different bases, then bringing this down, m times the log of a, bringing this down is equal to n times the log of b. So we're going to use this anytime we have two powers. Now it's quite a process, so let's go through this partially completed solution and see all of the steps. So let's look at all the steps and analyze them. So first thing is we have two different bases here, so we take the log of both sides and then bring the power down. And you can see that's what we've done in this step here. Then what we're going to do is use the distributive property. Log 3 is just a number, so we're distributing it inside the brackets. And then what we want to do is get x on both sides. So you can see that's why they subtracted 2x log 3. So now all my x terms are on one side. I want to then factor an x. So they have a common factor of x. I take x out, I'm left with 3 log 6 minus 2 log 3. This is just a number. So what I want to do is divide both sides by that number to get what my answer is. So this would be my answer as an exact solution. That's what x is. I have no idea what that number is, so it's really useful to put it into the calculator to get an approximate solution, which is what I do here. So x is approximately negative 0.3. Exact, no decimals, approximate, rounded answer with decimals. So whenever you can, use Bay because it's so much easier. So when I have one power, use Bay. If I have two powers, I have to take the log and bring the exponent down. So when solving exponential equations, there's three different things that can happen, and we want to do them in this order. The easiest way is using the same base. So that's my first thing. Write both sides at the same base, drop a base. If I can't do that, and I have one power, use Bay. And last, and save it for the last, take the log of both sides to bring the power down. Okay, we're going to omit class example number 4. because we only have to log when we have two powers. Let's look at class example number 5. So I have 4 to the x plus 2 equals 7 to the 2x plus 5. So by taking the log of both sides, I can bring the exponent down. So bring the exponent down, and that's the log of 4. Bring the exponent down, multiplied by log of 7. Okay, and now it's just a matter of distributing this number in. Log of a number is just that, it's just a number. So I have x log 4 plus 2 log 4 equals 2x log 7 plus 5 log 7. So everything that has an x, I just want that on one side. So I'm going to subtract. Let me actually just use a different color so we can see what we're doing here. So I'm going to subtract 2x log 7 from both sides. That's gone. And let's get this on the other side. So I have all my x's on one side, all my numbers on the other, and then that's gone. Okay, so here I can't combine these because they're not the same thing. Log 4 and log 7 aren't the same thing, so I'm just going to leave them just like that. And on the other side, I have 5 log 7 minus 2 log 4. So on the left-hand side, I have a GCF of x. So I'm going to factor these x's out, take it out. And what I'm left with is log 4 minus 2 log 7. And that will be equal to 5 log 7 minus 2 log 4. Okay, so again, I've just multiplied x by a number. So to get it by itself, I'm just going to divide both sides by that number. Okay, so that's gone. So x is equal to this big number. Okay, so if I ask for an exact value or an exact solution, that's what I'm looking for. But I always like to put it into my calculator just to kind of see what is x equal to. So putting that whole thing into my calculator like that, I can see that x is approximately negative 2.8. So this is an approximate solution. So that would be my whole solution. Now, I don't want to do that unless I have to. So the only time I do that is if I have to. And you can see that we got what we were supposed to get. So we're going to omit class example number 6. That is not part of the curriculum, which brings me to my summary. So I want you to write exponential equations with the same base on both sides and drop a base if you can. If you can't write the same base on both sides, that's when logs come in. So first choice, if I have 1 power, use bay. If I have 2 powers, then log both sides and bring the exponent down. So that's the end of this lesson. You guys can work on the assignment. I have detailed solutions on D2L. And that's the end of this video, and we'll see you for the next one.